We can start. Good afternoon, everyone. I hope everybody is well fed and ready for the next session. It is my great pleasure to introduce Gerard. So I saw like in the morning people are talking about simple and derivatives of simple. So he is one of the original authors of Simple and winner of multiple awards, best paper awards. He's currently a professor at University of Tübingen and a core faculty member of the Tübingen AI Center. Uh, Without further delay, I'll just hand the stage over to Gerard and have a nice time.
Yeah, thanks, Subik, for the introduction. Can you hear me well? Yeah, the back also. Yeah, it's a great pleasure to be here. Lately, I've been giving like talks always after lunch, and I know it's tricky if some of you like kind of fall asleep. I will not take it personally, and if you don't, then I consider this is a success for my talk. All right, so for today, I want to talk about how to learn large-scale 3D human and object reconstruction models, and in particular, I want to focus on the question on how to extract 3D information from these foundation models. So this is what I prepared for the talk. Like first, I will talk about work that is called Human 3D Fusion, in which is on extracting 3D geometry and appearance of people leveraging foundation models heavily. Then I will present like the state of the art on human pose and shape estimation, which is called neural localizer fields. And here I will emphasize on the importance of building models that are flexible in the inputs and outputs that they take and they output. I think nowadays it's very important that we don't train models that are just, one purpose, X to Y, but they should be more flexible. I will talk about synthetic data. I mean, we've seen like several talks on that topic this morning. And I will emphasize like the importance of synthetic data, how it can be combined also with foundation models. And at the end, if there's time, I will talk about how we can use generative AI for evaluating current models. All right, so let's get started with Human 3D Fusion. So here we address, this is work primarily by Yushuan Xue, who is a PhD student in my group. And basically, here we address a classical computer vision problem that has been looked at for many years. You have a single image, and you want to reconstruct a 3D avatar, including geometry and texture. So this is some of the results that we obtained with the model. And just to tease you a little bit, this is the reconstructions we can get. So true, we worked on the simple model. This doesn't use the simple model at all. This is like model-free, which brings some advantages. For example, we can deal with kits like here or very complex clothing, as you can see here. And I emphasize here, the only thing that the algorithm sees is just a single image, and the output is hallucinated by the model. This is a very hard problem. I mean, I don't need to convince this audience that humans are complex because they have different body shapes, they have different textures, clothing types, different accessories. And it's very difficult to model all these things correctly and get sufficient data for this. So, of course, there's a lot of excitement in the community with foundation models, and we're also excited. But we all know that a lot of these foundation models, they work to generate images. They produce beautiful images, but they don't know so much about the 3D world. And so what some people did is like say, well, we have some 3D data sets. We can fine-tune these models and train them to produce multi-view images conditioned on one image. So here the conditioning image is XC, and you can train a diffusion model to produce multiple views of this. And this is called multi-view diffusion. So this is cool because this is actually already closer to a 3D representation. However, when we look closer at the results, you see ghosting artifacts at the limbs, like things don't align pixel-wise. So if you would attempt to reconstruct this with triangulation, you would end up with an avatar that is kind of blurry because things are not pixel perfect. It's really, really difficult for these models to produce pixel perfect results. So some people said that, well, okay, what we can do is take these views and then train a sparse reconstructor, right? And then produce Gaussian splats or NERF or whatever. The problem of doing this is that, you're trying to fix errors. You're trying to fix problems when they're already there. You're reconstructing from images that are already not multi-view consistent. So still you will have some sort of ghosting artifact, especially at the limbs where, where the multi-view images do not match. So we looked closer at this problem. And here's a basically depiction of what we think is going wrong here. Basically, in diffusion, you go from a signal xt that is noised to the ground truth signal x0. And you take a number of steps. And in each one of these steps, these xt's are multi-view images that are not consistent. And so basically, what we thought we could do is like consider the ground truth, like real multi-view images that come from real 3D data. And basically, at every step of the diffusion, we'll project to this manifold of 3D consistent data. So that's the idea. Every time we do a diffusion step, we will project back to the 3D consistent result. That's at a high level, like how we address this problem of inconsistency of multi-view diffusion. So graphically, what we have is actually a 3D generative model based on Gaussian splats on the left that will be synchronized with a 2D multi-view diffusion model. And they will talk to each other such that the 2D multi-view diffusion will provide a strong prior for the Gaussian splat generative model, and the Gaussian splat generative model will produce an explicit 3D representation that will guide also the multi-view diffusion to be consistent. That's the high-level idea, and this is the diagram of the method. So there's a lot of moving pieces, but let me guide you here. So this is the diffusion process. You start with a noisy signal, and you want to obtain the clean signal. In this case, we're interested in the Gaussian splat representation. That's the output of our model. So in one step of denoising, you typically try to predict the noise and subtract, right? In our case, we have something a bit more involved, because instead of just predicting noise directly, we will go to 3D first. So this is how it works. You start with the noisy image in this current iteration, and the input. This is the input view from which we want to reconstruct, all right? Then you pass this through multi-view diffusion, and you obtain multi-view images that, you know, might be 3D inconsistent at this point, but they provide a strong prior. And then we send these images to the 3D generative model, along with the noisy images, and the 3D generative model has to produce a 3D Gaussian splat representation based on this information. And now, because we have a 3D representation, we can render it. Rendering a 3D representation will always be multi-view consistent by construction. And then we can backpropagate through the 3D generative model and the multi-view diffusion. And then we can iterate this process in a way that we are not fixing errors at the end, but we are iteratively correcting errors. And these are like some of the results we can obtain. We basically fine-tune a foundation model multi-view diffusion using this pipeline on a few thousand scans. And I'm convinced that this generalizes way beyond the scans. We don't have people wearing kimonos. We don't have people like wearing this kind of objects. We certainly do not have brides in our data set, but with this reconstruction model, we can deal with this complexity. So we have leveraged, we have squeezed out, we have distilled this 3D information from the foundation model while still being multi-view consistent. So actually, like more classical approaches, or I was going to say like people are like more prone to classical methods, I should include myself also in some way, might ask, okay, how does it compare to a model that leverages simple? And of course, simple cannot model like things like wedding dresses and objects and so on. There's some models that have adapted simple to be more robust to this kind of clothing, but still, they still struggle. Like these are models like Icon and Econ that are like the state of the art on this type of reconstruction. And this is another example that I really like. Like there's this little girl holding the wall like this, and when the model can hallucinate that there should be some arms holding the wall. And I really think this generalization power comes from the foundation model. We can deal with also more complex objects like Ninja Turtles. And the model, of course, it has nothing specific to humans here. So we also use this model to reconstruct objects. This is work that is coming, and is also much more consistent than the state-of-the-art multi-view diffusion and also video diffusion. This SV3D is a very strong video diffusion model that has no 3D representation. It's basically a neural network that querying the camera produces multiple views. And you can see that, if you have a 3D representation, you have things for free, like consistency is for free. It has its limitations, right? Resolution is tricky. You might see that this lion, it doesn't look quite sharp, but we have addressed this problem by now also. All right, so some more results here, like, you can deal with a woman that is pregnant or even a woman like with a baby. It's not perfect. You can see here that, the baby geometry is kind of flattened. But I was really impressed that, this can deal with two people, and we never trained for two people like specifically, right? It just arose naturally because this framework is not specific to one human. Here's just a few more examples of different objects and humans that we can reconstruct with this, what we call like human 3D fusion, and the new version is, how did we call it? Gen 3D fusion? I forgot. All right, you might say, these faces don't look so sharp. I cannot use this in production. I cannot put this into a video game. And I agree with this. I take it. Now, just a teaser. We haven't solved the problem completely, but these are avatars that we can generate from scratch without any scanner or anything. So, and it's still not like at the quality of like, super Visual Studio, but it's getting there, right? I mean, notice like this, like wrinkles and these details in the face. And these are avatars that you can generate infinitely. You can generate infinite avatars. This is a different method. But I just want to show a teaser that we've addressed some of these resolution problems. All right. I guess we want questions at the end better, or yeah, it's better. All right. I'm not going to talk about this work, which is featured to Gaussian splat, but I just wanted to put it here so that if you're interested in knowing which foundation models, which we have many, Dino, Radio, and Dino V2, Midas, SAM, Clip, whatever, Duster, Master. If you want to know which ones are the good ones for extracting 3D information, we have a methodology to evaluate this. And we compare a lot of different foundation models, and we look which ones are good for texture, which ones are good for geometry. And so you might check this, which is coming at CBPR this year. All right. This was focusing more on appearance. This model that I've shown before, if you show it like very complex poses, like yoga pose and so on, it will break probably. And so now, like, let's focus more on like how to track people, how to estimate their motion. This is also a classical problem in computer vision, very related to the other one. We're not so much interested now in the clothing per se, but more in the motion. And this is work, joint work with my postdocs, Ishvan Sarandi. So we notice there's an explosive growth of data sets. This is good news, but the annotations are very heterogeneous. Different people use different annotations for the avatars, as you all know. So the goal at training is to leverage this heterogeneous data without having to do data conversion. And the goal at inference is to flexibly choose which output the model will produce, right? And so if we look at some of the data sets, we have more and more data sets, which is really good news. However, when we look at the annotations, we see like a zoo. You have some people use simple, some people use simple X. Microsoft has its own model, like Meta has another model, like Google another model. Like this 3.6X uses like some key points. Some people like to annotate like landmarks on the face, some people on the hands. It's endless. And it's fine. It should be like this because people have different needs, right? Now, the classical approach would be to put everything into a common format and then train from this. But this is like tedious, it's time-consuming, and prone to error. And it's also a nilpost problem. To go from one skeleton to another is a nilpost problem. So what's the idea here? Like, we're going to think of pose estimation as a point localization problem. So we're going to consider the volume of a human body, and we're going to consider points. Any point on the surface or the volume is something that we want to predict from the image. And now the user will select which point you want to predict. And this is going to give us a lot of flexibility. So, right, so before we move into this localizer fields idea, the standard way of predicting, like how many of you have worked on pose estimation? Can you lift your hand? Oh, quite a bit of people. So the standard way, what we've learned over the years is that you can have a vision backbone, have feature maps, do convolutions, and then get heat map logits, and then do soft Armax to detect where the predefined joints are on the image, right? Like the elbows, the shoulders, and so on. Now, if I have like 14 joints, here I will need like 14 heads. Yeah. What should I do if I want to predict 28 joints instead of 14? Well, I should have more heads, right? 28 heads. But what if I want to predict 100 or 1,000 joints? Well, I'm going to need an insane number of parameters. And also, these heads are not going to talk to each other. So it's like kind of not, it seems like we can do something better. And we have to pre-decide the skeletons, which is also not nice. So here the idea is like we borrow this idea of neural fields, but now we're going to have a neural field of neural networks. So basically, like we're going to choose which point, the canonical point on the surface or on the volume. And this network, which is a meta network, will predict the weights of a neural network that will detect like this particular point in the image. Now, why is this cool? Because now I can choose any point on the body, and this produces the weights. So I don't need to increase the number of parameters. The number of parameters is fixed. And also it has another advantage. Because like these weights are predicted as a function of the point. Now, if 2 points are close to each other, the neural network weights, the detectors, will also be close to each other, right? So this gives us like a smoothness in parameter space of networks. So that's the idea. Like you have this meta network that predicts neural network weights that will predict these joints. So this is the formulation. It's not different, not very different than like a standard thing, but now we have like for training this from different data sets. If we had infinite data, we would have this volume integral over all points in the body. That's where you have this volume integral over the 3 dimensions. And then you want to minimize the ground truth post point, G of P. This is the ground truth point. And the predicted point by our localizer field, right, in post space. In practice, some data sets will have sparse key points, some will have only the eyes or whatever. And so we evaluate this integral for the data we have, for the points we have, right? And for the rest, we don't evaluate. And we just train this as supervised learning. All right, so let me show you this in action because otherwise maybe it's not clear what we're actually doing. What I'm going to show here is on the left, I'm going to show a user that selects the point that needs to be predicted along the body. And on the right, you're going to see in real time or at interactive rates like this point predicted. Right, so here we're selecting where we should predict the point, and then this is like the network is predicting the point. Also, like here we have this for 2 people and also like for a video. Yeah, so a colleague of mine told me that we should have called this pose estimator the colonoscopy pose estimator because it looks like a colonoscopy, and so on. All right. Just very quickly, if you're interested in estimating simple parameters from a mesh, we have a very fast way of doing this, and the code is like separated, so you can use it quickly, and it works nicely, and it's much faster than what was there before. If you're interested in this, getting simple parameters from meshes. All right, so now you might say, okay, this is all very nice, but how does it actually work? And because we have trained from a lot of data sets, and because the network has this like implicit structure, this works very robustly for human pose estimation. It works for multiple people. We need to detect people and then run this NLF on each of the windows. And one nice property is that it snaps better to the silhouette, so it estimates the shape better than than all the previous pose estimators. And now this is the state of the art in pose estimation. So I believe this is like relative to camera. Now Istvan has adapted this to predict also the camera pose over a video using some structure from motion. Like he has the pipeline on the code, so you can check the code. He recently put like 2 weeks ago like an update. All right. So again, the message here is that we have the state-of-the-art pose estimation from pose. We have this state-of-the-art pose and shape estimation, but the main message is that we have been able to achieve this because we have been able to observe a lot of data sets, right, in their native format without having to convert, and this is very beneficial. All right. Emphasizing again on like this flexibility of inputs and outputs of models, I'm going to switch gears a little bit and like show some work that we've been working on like modeling 3D humans and their interactions with 3D objects. And so in reality, what we're interested is in modeling the joint distribution of human, object, and interaction type, right? Given one object, I can interact in many different ways. I can move a chair or I can sit on it. This is what the variable I encodes. And we have a lot of models in the literature for modeling the human condition on object or even the object condition on human. But here we wanted a flexible model that we can go in any direction. We should be able to produce samples from the joint distribution. So human, object, and interaction. We should be able to produce also human and interaction given the object. Everything that is in blue is given to me, and everything in green is predicted by the model. Or we should be able to, define interaction maybe with text, maybe indicating which body part should be in contact. And the model should be able to produce the object or the human or the interaction, and in any combination of those, right? So you have 7 possible combinations, and you don't want to train 7 different models. How do we do this? Like diffusion is really cool for doing this, because I don't have time to go into all the detail on how to encode the objects and so on, but the basic idea, which is powerful, is like to say, well, I will train such that, when the human, for example, like is not observed, then I will add noise for those variables, and I will unmask the other thing. And the idea is that, if it's the object that is not observed, then I'm going to add noise there, and let the network see the object variable. And so in a way, we think of this as like a switches, right? And whenever it's unobserved, you have noise, and whenever it's observed, you have the variable. And you train with these different schedules such that the network learns all the conditional models with a single model, right? So you might have that that the object is observed, in which case human is noised and interaction too, and you might have that the everything is unobserved, in which case everything is noise, and so on. And like this, having these switches, you have the 7 combinations. And now let me show you some results. So you can, for example, give the object, like give the chair, and ask the model to produce different sitting configurations for that given object. Yeah? Or conversely, you can give the human and ask which object poses fit this human. Here's another example. This is a single frame model, and so what we did to create this animation is to some sort of keyframing. We do it for given frames, and then we interpolate the poses in between. It's not a dynamic model. That's something that we should work on. So this is another example where here the human is seen and the object is predicted by the network. So in a way, this is giving us understanding of how the human and the object interact with each other. Here, the main bottleneck again is of course data. We have a few data sets, but much more data is needed. We have other examples where we use a method by Tripathi and colleagues. Maybe Dimitris will talk about this later. I'm not sure. So basically, this is not our work, but what they did is like to train a model that would predict the contact maps given an image. And we can directly use these contact maps, right? And the human, right? Here we predict the human and the contact maps by an external method. And we can, using 3D, we can predict what plausible objects go with this kind of contact maps and humans. So you can see how you could use this as a prior for understanding what people are doing in 3D scenes. All right, another example of like a model that we have flexibility in inputs and outputs is Unimotion, where we go from text to motion or from motion to text, and the motion is perfectly aligned with the text. So a lot of these text to motion models, you type like, person dancing yoga and then running and then grabbing like a glass of water. But you don't have control of when things happen. And if you're an animator, you want to have control of when things happen and where, and you want to, or for example, if you want to deploy these motions to a robot, this is super important to know when things are going to happen, right? And so here, what we did is to train a model that could have this alignment of like the text and the motion. So whenever the user can control when the switch should happen, right? So you basically have this control. This is also just a teaser. Like you can also go the other way, like you can give the motion and the model does the captioning for you. Yeah, but I will not explain this in detail. All right. So I have 28 minutes on my, that's correct, right? Okay, just to make sure I didn't do it. All right. Of course, like we're ultimately like people always move to interact with the 3D world, to move objects in the 3D world, and we're very interested in modeling humans and objects. So here, as the models before, we want to reconstruct the human, but also the object. And here I'm going to emphasize on the importance of synthetic data, because here we're really bottlenecked. We don't have data sets and foundation. We haven't figured out how to use foundation models to solve this problem. Here we have a lot of problems. We have like depth scale ambiguity. We have heavy occlusions. We have diversity in human poses and shapes. But now it's even more difficult because the human occludes the object occludes the human. It's even more tricky. So we need some priors of interactions and shapes to solve this ill-posed problem. So we have a lack of data. So we have existing real data sets like Behave or Intercap. This is something we captured with 4Kinects, and we had a bit of user annotations to make sure that the poses of the human and the objects were correct and so on. And it's cool, like people are happy with these data sets, but still, like, the scale is like what, 7 humans, 10 humans, 20 objects. It's not really at the scale of like that is needed nowadays, right? But then we have like other data sets which are synthetically generated, like Bedlam or Objaverse. Objaverse has been immensely useful for training this multi-view diffusion model, right? This has like about 10 million 3D objects. So how can we leverage this data? So the key insight here is to procedurally, it was talked about this in this morning, that how to use synthetic data to multiply the effective data. So we have human data sets, we have object data sets, and we have interaction data sets. Well, we can mix and match and have multiplicative scaling, and then have this procedural generation of human-object interactions. And that's essentially what we do. I thought this was a video. Oh no, it's not video. We generate like 1 million synthetic interactions of humans and object shapes. This data set is available. I mean, all the models are available for research purposes. And here we had to address the problem of how do you actually change the object of a human. And so I don't want to spend a lot of time on this, but the idea was that you had to identify where the contacts happen on the object, do registration, transfer the contacts from one object to another, and then basically replace finally the objects like once you know the contacts. Yeah, once you know the contacts where they should go, you can do inverse kinematics. And by the way, like in terms of registration, before you try anything fancy, I recommend you just train using a lot of data, an autoencoder that predicts a fixed number of points, because we've tried this with objects and with humans, and what happens is naturally the points are kind of registered. The network learns that, you know, the right corner of the leg is always the point number 100 or whatever, right? And so this is a very simple baseline for registration that is very effective, and that it beats, in my experience, like baselines that are much more complicated. So this code for registration you can also find along with this paper. All right. Yeah, here's the video. So this is the data set that, if you're interested in this, you can check out. You have like millions of interactions of humans and objects. And from this data, we train a diffusion model that is also based on point clouds, that they start with a point cloud of Gaussian point cloud, and it's diffused to the human and the object. Now, in the interest of time, I'm going to skip these details. And what is interesting is that we had the previous work that used a template of the chair to reconstruct, and now we don't make any use of the template, and we can reconstruct even better than our prior work. And the model works also for images in the wild, and it can produce like this point cloud for the human and the object. Right. We extended this to dynamics, to motion. This is some work that is called intertrack. And so here's like the result that I've shown before. And what happens if you do single frame estimation, you don't have like temporal coherency, it's noisy. And also the point cloud, the points keep switching. You don't know what is what. You don't have correspondence. Yeah. And so with the new method, we have like coherent point clouds, like this is like points that come from the simple model, and an object shape that is more detailed because it leverages the temporal information. I don't want to overload you with the technical details now, but we can talk about this if you're interested, or you can shoot me an email. So we extended the previous data set to dynamic motions also, using similar principles, and then basically we have extended this to dynamics. And the idea, just very quickly, is to consider a global shape of humans and then basically register every single point cloud that you get at every frame to a common template. And for the object, you have something similar to what is known as fusion, right? You basically fuse every new input frame that you have into a canonical shape. And yeah, so these are some comparisons. This is the previous single frame method, and this is the method that takes into account dynamics. And we can track this human-object interactions nicely. Of course, these motions are still quite orchestrated, right? I mean, my dream is to capture a room like this and people talking and, like, you know, or having dinner together with the objects moving and so on. We're still far from this challenge. But we were quite happy because, like, without making any use of object shape knowledge, right, it can reconstruct the shapes quite nicely. Here's another example of the human and the object reconstruction. Of course, this is just human object, but we might be interested in full 3D scene and humans, and this is also something that we're working on. This is just a teaser. I'm not going to tell you the recipe to solve this problem, but as you can imagine, this is a hard problem. So here we're reconstructing both the human and the 3D geometry and making sure that the scene is coherent with the geometry. This is another example. You might recognize this person. Yeah, so this is really exciting, and I think slowly we'll converge to, having like this virtual avatar work much closer to robotics than it used to be. All right, how are we doing on time? Maybe I should conclude? Yes, I will conclude then. I will skip this GenAI as benchmarks. I just want to mention that we can use GenAI to generate pretty pictures and videos, but maybe we can also use this for evaluating how well pose estimation works, or how well like our systems will work in the real world. And that's something that not so many people are looking at, but we have control now. We can say, I can change the gender or the body shape, the clothing, and so on. And I can see how different pose estimators actually do under these conditions. And then you can evaluate which methods break under which conditions. Unfortunately, none of the reviewers are convinced by this. It seems like they only want methods. But I think we should also think about new problems or new ways of using existing technology. We don't need to create so many architectures. We don't need like 8,000 architectures. But that's a different topic. Anyways, in conclusion, so we have that, I've shown that image and video foundation models, they contain a lot of 3D knowledge. And if we are, clever about it, we can extract this 3D information. The data sets are increasing. And with this, we should build models that are flexible in inputs and outputs. And I've presented neural localizer fields that can deal with any skeleton format, and 3D that can predict humans, objects, and interactions in any direction. And then finally, I've just shown a very brief teaser about how GenAI can be used to evaluate the robustness and safety of current algorithms. And last but not least, I thank my students who are really the ones doing all the work. I'm just presenting it, and I'll be happy to answer questions.
Yeah.
Can you hear me? Not sure if this works, but I'm going to throw my voice if possible.
I hear you.
Thanks for the talk. I have questions relevant to the first axis and the fourth axis of your talk. So one of my PhD students, she's working on the generalization of the poses across two different things. So one is just restrictive to the upper torso.
Yeah.
And simple or simple X, it doesn't really work. It has artifacts when it tries to, even with pose standardization, it has issues when it's restricted to just the upper half of the torso.
You mean like estimating from images?
From images in real world domain.
Like with but you're talking about our method, like neural localizer fields, or a different method?
Like, for example, you showed icon and econ in your comparative results. So even with that, there are issues that it has artifacts when it tries to show the poses, generalizes the poses, restricted to the upper human
those
torso.
are not our methods. I suspect that, the neural localizer field works fine with cropped humans. I've seen this, there's no problem. The human 3D fusion would struggle, I think, if you have crops. Unfortunately, the boring answer is that the way to deal with this is to train with crops.
Of course, and that was one thing I was trying to circumvent. And quickly, just to follow up, the second one relevant to the fourth axis of your talk is about the generalization across domains. So for example, in anime, where the data is restricted now. So are there ways that you think that could solve that issue of generalizing poses across domains?
You're talking about pose estimation, or you're talking about the full 3D reconstruction?
The poses, but across the domains.
I would have to try, but I mean, I've seen like the pose estimator work with like cartoon characters, and also I've seen reconstruction. I mean, like what we saw, like the Ninja Turtle and so on. So this seems to be less of a problem if the anime is not completely, really strange, but because the foundation models have seen these shapes, and so.
Okay, thank you.
Okay, we can have one more. Yeah.
Yeah, thank you for the talk. In the first bit, you'd mentioned you had interactions with two people kind of forming naturally. With the later work on like the human-object interaction, did you try anything with like human-human interaction, having multiple humans instead?
Yeah. I mean, that's something that we're very interested, and like to some degree we can deal with this. I mean, if you're talking about estimating the human poses, like when it breaks is when you have two people hugging and you have complete occlusion. That's really tricky. And it's not. I'm not sure. I have ideas on how to address this problem, but you don't want to deal with like have priors for every possible combination, because this is not scalable. But if the interactions is like not very close, or like for example, like, we can track people dancing, but if like it's heavy occlusion, it will break. Yeah.
Thank you.
We can have one more quick question. Otherwise, let's thank the speaker, and you can ask him further questions.